Hey guys, this is Professor Janacek, and I want to go over an example of implicit differentiation. Remember, for implicit differentiation, you do not have to isolate y before you get started. So let's go ahead and take a look at example 4 here. We want to find the slope of the curve. 2 times x plus y, quantity to the 1/3 power, is equal to y at 4, 4. So what this means, finding the slope, here we go, finding the slope of the curve. Remember that what that really means is to find the slope of the tangent to the curve at that point. All right, so slope of the tangent, of course, means the derivative. We're trying to find dy dx. And we'll evaluate that at the point 4, 4. All right, so let's see, what do we have? Since, to begin with, you know what, I'm going to go ahead and turn this around. We like to have y on the left-hand side, so we'll start with that. It's not necessary, but maybe it makes life a little bit easier. All right, since we have that, then we know that we could take the derivative of this with respect to x. Well, on the left-hand side, that just gives us dy dx. All right, that's nice. On the right-hand side, I've got a couple of things going on. I'm first going to have to use the power rule, but also the chain rule. Power rule, I still have that 2, and then I bring that 1/3 down to the coefficient, and then we keep this inside as is, and then that exponent 1/3 will subtract 1. That gives us -2/3. But now the chain rule says we need to take the derivative of the inside stuff. Inside, I've got the derivative of x. With respect to x, that's just 1, but then we've got the derivative of y with respect to x. That's dy dx. So what I've got now, let me go ahead and I'm just going to take this bit here and distribute it. In doing so, I will go ahead and multiply 2 times that 1/3. So that gives us dy dx is equal to, well, times 1, that's just 2/3, times x plus y to the -2/3, plus 2/3 times x plus y to the -2/3, times dy dx. All right, that was a simple distribution. All right, just so you know what's going on here, notice I still have dy dx on the left-hand side, but those negative exponents, yeah, they're both negative exponents. I can actually move those to the denominator. So that gives us 2/3 times x plus y to the -2/3, or to the +2/3 now, plus 2/3 times x plus y to the +2/3 times dy dx. Now the idea is that I want to get these dy dx's together. Oops. This one and this one. So I'm going to go ahead and combine those terms. So we have dy dx minus 2/3 times x plus y to the 2/3 dy dx is equal to 2/3 times x plus y to the 2/3. And now I see that I have a dy dx in both of those terms. We'll factor that out. That gives us dy dx times 1 minus 2/3 times x plus y to the 2/3. Still still equal to 2 over 3 times x plus y to the 2/3. Now if we isolate that dy dx, that means we'll divide by 1 minus 2 over 3 times x plus y to the 2/3. That gives us the stuff on the right-hand side divided by the parenthetical stuff on the left-hand side. All right, well that's an answer. However, this is a complex fraction. Not real crazy about having complex fractions in here, so what I want to do is to simplify this complex fraction we'll do that. In this case, we simply need to multiply by the common denominator for that form of 1. So the common denominator over the common denominator. And if we do that, well, we get dy dx is equal to, in the numerator, oh, that reduces to just a 2. In the denominator, notice I'm going to take this and kind of distribute it to each of these terms. So that gives us something that looks sort of like that. All right, there we go. So that's dy dx. However, we need to evaluate this at the point 4, 4. So simply replace x with 4 and y with 4. Let's see if I can clean that up a bit. So, dy dx evaluated at the point 4, 4 ends up being, oh, let's see. Oh, simplify that. The cube root of 8 squared times 3. Subtract that 2. And then reduce that whole fraction. Oh, looks like that's going to be a 1/5. So there you go. All right, enjoy.